How are you all doing today?
Doing well.
Pretty good.
Were you able to view the video lecture that I posted on Saturday afternoon?
Yes, sir.
Yes, sir.
Yes, sir.
Cool deal. Does anybody have any questions about any of that content? Alrighty, nobody is speaking up, so let's see what's going on in chat here actually. All right, just people saying yes. Cool deal. All right, so I've prepared an example problem then. This may be a little difficult, which is good. And then we'll go through that, and then we'll take a look at the in-class assignment problems and try to work stuff. And then if you guys have any questions regarding anything we've talked about or any of your upcoming homework problems or anything like that, I'm happy to answer them. So to that end, let's share this. All right, so this is a kind of beefy problem that will hopefully help to reinforce the passive sign convention, as well as apply some of the basic circuit analysis rules that we'll be using in this class. I tend to spend a little extra time on passive sign convention just because it's something that a lot of students seem to have difficulty grasping at the beginning, and it's actually rather important because if you don't understand it fully, you'll make a lot of simple mistakes that will just cause you endless amounts of frustration. So the goal in this problem that I have prepared is to determine the value Vx, which if you can't locate it, I'll go ahead and circle it. So we want this voltage, the voltage drop over element C for our circuit here. And one thing that makes this problem particularly difficult is that there is a dependent source also in the circuit, and it depends on that voltage Vx as well. So that's going to make things a little more difficult. So what we are going to do is we are going to determine the power absorbed by every element in this circuit, and then use that to develop a relationship that will allow us to solve for the quantity Vx, okay? So the power is by definition, sorry, no, that was right. Sorry, my hand got in the way. I times V, right? Because we want absorbed power, what we're specifically going to be looking for is when the current is flowing in, or what current is flowing into the positive polarity terminal of each element. So let's start by looking at our 12-volt voltage source. So the power absorbed by our 12-volt source, okay? So that current of 2 amps, does it flow into the positive polarity terminal or the negative polarity terminal?
Negative.
Negative, okay. So that means that the current flowing into the positive polarity terminal is going to be what?
Negative 2 amps.
Right, negative 2 amps. So if we want to change the direction of the current, we simply change the sign of the magnitude. So the current flowing into the positive polarity terminal is negative 2 amps. The voltage drop over the 12 volt source is 12 volts. And so this guy is absorbing negative 24 watts of power. Pretty straightforward, I hope. Let's move along to element A. So it has a current of 2 amps flowing through it. and that 2 amps is flowing into the positive polarity terminal. So we should have 2 amps multiplied by 4 volts, and I'm not going to need to add an extra negative sign because I don't need to change the direction of the current. And so I should see that this is absorbing 8 watts. Hopefully fairly straightforward. Let's do our dependent source. So we have a current of 2 amps flowing into the negative polarity terminal. So we're going to have negative 2 amps multiplied by the voltage, which is 2 Vx, gives us negative 4 Vx watts. This is going to be one of the expressions that helps us define that unknown voltage Vx. We have, oh crap, we have 2 12-volt sources in here, so let's call this one left. So we have another 12-volt source. Call that 12-volt right. A current of 4 amps is flowing into the negative polarity terminal. So we're going to have negative 4 amps times 12 volts is equal to negative 48 watts. We have element B, where 2 amps is flowing into the positive polarity terminal of the 16 volt. So 2 amps, 16 volts, 32 watts. We have element C. 2 amps is flowing into the positive polarity terminal, so we're going to have 2 amps times Vx. It's going to give us 2 Vx. And finally, we have element D, where we have 2 amps flowing into the positive polarity terminal. So that's 2 amps times 20 volts is equal to 40 watts. And if we add all of these powers together, the sum should equal to 0 because of Telegen's theorem. So we have negative 24 plus 8 minus 48 plus 32 plus 40. So that's 8. And then we have minus 4 Vx plus 2 Vx gives us minus 2 Vx is equal to 0. So solving this guy, Vx is equal to 8 divided by negative 2 is negative 4 volts, if I did my math correct, which I believe I did. No, I didn't do it. It's positive 4 volts. If I move 2 Vx to the right-hand side, divide both sides by 2, 8 over 2 is equal to Vx. Yeah, okay, that's right. So, I don't know, we went through that pretty quick, but hopefully that helps solidify a little bit of the passive sign convention stuff. Did anybody have any questions regarding that example?
Could you scroll up a little bit to see B? Thank you.
Any other questions or comments or anything about this guy? Nobody's saying much anything. All right, well then, let's go ahead and jump over to the in-class assignment then. And let's go look at problem 1.
This in-class assignment, do you want us to write it down and then scan it PDF and then upload it to Moodle?
Yes, and I will put a, I'll make an online submission portal for you guys to be able to do that immediately after we finish up here. And for those students who are listening in or watching on YouTube or whatever because they can't attend class, what I'm going to do is I'm going to have the in-class assignments due like 2 days from when we go over stuff. So today's Monday, so it'll be due Wednesday at, I don't know, noon or something. I'll make up some arbitrary time to set it at, but if you're unable to attend class, you won't have to just break your back trying to catch up immediately, I'll give you a little bit of wiggle room. Does that sound reasonable?
Do they
Yes,
have
sir.
to be uploaded as PDFs?
Yes.
Okay.
So if you're doing it on a tablet or anything like that, you should be able to use just Microsoft Print to PDF. It's part of the Office suite or whatever you're using. If you do not have, like if you're not doing it on a tablet, you're doing it on your phone. If you have an iPhone, I know that you can go to Notes. Give me a second. And you can create a new note, which I got to find the button for that. Well, actually, when you go into Notes, and the bottom and the middle, there's a little camera icon. That is effectively you using your phone as a scanner. So you can take pictures of documents and it will automatically convert them to PDF files if you tell it to. I believe there's similar functionality for Android phones. And if there isn't, you can download applications like Cam Scanner, which is free and does that exact same thing. Just takes a picture of a document and then stores it as a PDF file. So should be fairly straightforward to get everything together as a PDF. Okay, so for problem 1 here, we're told that the charge entering the positive polarity terminal of a circuit element is given by the equation Q as a function of time is equal to Im of t plus Qm sine omega t, where Im is 6.3 milliamps, Qm is 2.1 millicoulombs, and omega is 1.3 radians per second. And we're asked to determine the amount of charge that enters the circuit at a particular time and the amount of current that flows through the circuit at a circuit element at a particular time. So do any of you guys have any idea how we might approach part A?
First, maybe plug in the given and then convert the t into seconds instead of milliseconds.
Okay, so we're going to plug in the given information into what?
Into the given equation, the Q of t.
Right. Okay, so we're trying to find charge and we have an equation for Q of t, which represents the charge. So to solve part A, we do exactly what that gentleman suggested. We literally just plug in our numbers. It's that simple. So Q, dang it. Why was it zooming? Hold on, sorry. I don't like red. So 700 milliseconds is the same as how many seconds? Let's start there.
0.7 seconds.
Right. So Q of 0.7 seconds is going to be equal to Im, which is 6.3 milliamps times t, 0.7 seconds. That 3 doesn't look like a 3. I don't know why all of a sudden this is drawing terribly. Plus Qm, which is 2.1 millicoulombs. Stupid cables out of the way. Times the sine of omega, 1. Oh my goodness, this is driving me nuts. Radians per second, so that's just per second, times 0.7 seconds. All right, so unit-wise, we have a little bit of an issue here potentially because we have milliamps times seconds and we're adding them together to millicoulombs. So first, is that okay?
Yes, sir, because a milliamp is the same as a millicoulomb per second.
Exactly right. So 6.3 milliamps times 0.7 seconds gives us 4. Why my tablet is being so difficult all of a sudden. 4.41 millicoulombs plus 2.1 millicoulombs times the sine of 1.3 times 0.7, which is 0.150 1588. And so 4.41 plus 2.1 times that guy. So I got an answer of 4.443 blah, blah, blah. And I've made a mistake. So how many of you got the answer if you're attempting to follow along, got the same answer as me?
I got a different answer, sir.
I got the answer that was on the page.
Okay,
Yeah,
so
me too.
can either of you explain why you got that answer? And I know what the answer is, but I want to see if you know.
You have
Did
to. You go. I talk too much.
I was just gonna say, did you use degrees instead of radians on your calculator?
That is exactly right. So it's very important that you guys pay attention to whether you're working in radians or degrees. We are going to be working an awful lot of problems in this class where we're utilizing omega, which is an angular frequency, and it is, by definition, always expressed in radians per second. So it's very important that using your calculator, we're working in radians. And for the next part of the problem where we're going to have to take a derivative, if you were to take the derivative on your calculator with it set in degrees, it's going to give you a horrifyingly messed up answer. So make sure that you're working in radians, at least for the next probably 2 months of this class. So that should give me then 6.068 millicoulombs. All right, so that's the answer for part A. All right, part B, we want the current. How are we going to find the current? There were like, I don't know, probably 5 or 6 equations that I went over in my video. Which of those
Joshua.
is the right one?
Joshua says take the derivative.
Take the derivative. Okay, so we're going to take the derivative of the charge with respect to time. That's right. So I at 0.7 seconds is simply dq by dt evaluated at t is equal to 0.7 seconds. So what's going to happen? Let's see. So the derivative of Im of t with respect to t is simply Im. The derivative of Qm sine omega t, what's that going to be?
Qm times omega times sine of omega times t.
So the derivative of sine is sine.
My bad. I forgot about that. Cosine.
All right, so the derivative of sine is positive cosine. Are we all in agreement there?
Yes.
Yes.
Yep.
All right, so omega Qm cosine omega t. And now this guy evaluated at t is equal to 0.7 seconds. And so that's going to be 6.3 milliamps plus 1.3 per second times 2.1 millicoulombs, which that's going to be millicoulombs per second, which is going to be a milliamp. So everything's working out good there. Cosine of 1.3 per second times 0.7 seconds. All right, so 7.976 milliamps, which is, I believe, what the answer I got previously was. All right, so any questions about that guy? Hopefully fairly straightforward. Nobody saying anything?
Yes, it's straightforward.
Okay. All right. This guy's maybe a little bit more difficult. So we're told that the charge entering the positive polarity terminal of a particular circuit element is given by the equation Q of t is equal to Qm e to the minus alpha t, where Qm is negative 30 millicoulombs and alpha is 4 per second. The voltage present across the terminals of the same element is given by V of t is equal to Vm e to the negative beta t, where Vm is 120 volts and beta is 2 per second. We want to find the power absorbed by the element as a function of time. So how are we going to do that? We have an expression for charge and we have an expression for voltage. So what do we need to do?
You need to find the current from the charge equation by taking the derivative, and then
Okay.
you multiply it by the equation, or like whatever you get for voltage.
Okay, so what you are suggesting, which is correct, P of t is equal to V times I, where I is dq by dt. So that's going to be Vm e to the minus beta t times the derivative of the charge. So how are we going to take the derivative of this exponential function? What's the derivative of e to the minus alpha t?
Is it minus alpha to the e, minus alpha times e to the minus alpha t?
That's correct. So I've noticed a lot of students make a mistake there. When you take the derivative of an exponential function, you bring down the coefficient of the argument. And when you integrate an exponential function, which we're going to have to do a bit in this class too, you bring down 1 over the coefficient. So you're correct. So this should be negative alpha e to the minus alpha t. So that's going to give us negative alpha Qm e to the minus alpha t, like so. And we can simplify that a little bit further. Negative alpha Vm Qm e to the minus alpha plus beta t. When we multiply two exponential functions together, we add their arguments. So that would be e to the minus alpha t minus beta t, and I've just grouped that minus alpha minus beta to negative parentheses alpha plus beta. So everybody following my math here?
Yes, sir.
So now we can just plug in our numbers, which would be helpful if I could see them. So this is negative 4 per second times 120 volts times negative 30 millicoulombs. E to the minus 2 plus 4 is 6t. And let's see, so negative 4 times 120 times negative 0.03 gives me 14.4 e to the minus 6t watts. So to be clear here, I did another conversion, which I guess I can explicitly do over here, that says 1 amp is 1,000 millicoulombs per second. So that's why I multiplied by 0.03 instead of 30. But anyway. All right, so part B. How are we going to find the energy? Any ideas?
Well, energy can be found by taking the integral from 2 time points of the power, right?
Right, absolutely right. So we got our expression for the power, so now we just simply integrate that. So we're going to integrate from 0 to 0.05 because we need things to be in seconds. We're assuming here that t is a measure of time in seconds. So that would be 14.4 e to the minus 6t watts with respect to time. So now we're doing the exact same thing as I said people make mistakes upon. So we're going to have negative 1 over 6 times 14.4 e to the minus 6t evaluated at 0.05 seconds and 0. And so this is going to be negative 1/6 times, actually let's move that 14.4 out as well. E to the minus 6 times 0.05 minus e to the 0. And e to the 0 is not 0. That's another common mistake I see people make. And so I get 622.036 times 10 to the minus 3, which is a milli, and this is watts times seconds, which is joules. So units are important. Don't forget to take care of those guys too. Let's see if there's anything else here. I don't think there was, though. Determine the power and calculate the energy. All right, so that seems fairly straightforward as well. Just trying to really test you guys if you can remember how to do simple derivatives and integrals. So far in this single in-class assignment, you've been asked to take, I believe, the derivative of a sine function, and then an exponential function, and you're going to have, we've taken the integral of an exponential. As far as the calculus used in this class goes, it's going to be exponential functions and sine and cosine functions. So we're actually hitting all the high points really on this very first in-class assignment. Beyond that, I think I'm sometimes on exam 1, I might put a simple polynomial. So, you know, like 5t cubed plus 3t squared kind of thing, for you to either differentiate or integrate. But other than that, that's going to be it. So you should never have to go crazy with like, what is it called? Integration by parts or anything like that. It should fairly be straightforward. So, all right. And then this example problem here is very similar to the one that I worked at the top of the class. We want to calculate the power absorbed by each element in this circuit. So let's see. Let's start with a 36 volt source. I know what the answer is because it's written right above here, but how am I going to get to that? Let's start there.
E equals IV, 36 volts, and then 4 amps.
So 36 times 4 is positive 144. Where'd that negative sign come from?
Because it's going in the negative terminal.
Right, and we want the power absorbed. Okay, so just super clear about that. Because we're calculating the power absorbed, anytime the current is going into the negative polarity terminal, we need to change its direction by multiplying the current by a factor of -1. So that's -4 amps times 36 volts is -144 watts. All right, for element 1. What are we going to do for element 1?
4 times 12 volts positive.
Right, current's going into the positive polarity terminal, so we simply multiply the two together. That's watts, not volts. Let's see, element 2. What's going on there?
Just multiply them together.
You multiply it 2 times 24 because the direction of the amps are going down, which means it's getting absorbed to the positive.
Yep. So yeah, the current is flowing into the positive polarity terminal, so we simply multiply them. So 2 times 24 is 48. Let's see, our current control voltage source. So the current of 2 amps is flowing into the negative polarity terminal. So that means we have to change the direction of the current. So we're going to have -2 amps. And then the voltage is going to be 1 volt per amp multiplied by IX, which is given as 4 amps. So 1 volt per amp times 4 amps gives us 4 volts. So -2 times 4 is -8 watts. And finally, for element 3, 2 amps flows into the positive polarity terminal of the 28 volts. So that's 2 times 28 volts is 56 watts. And so we could easily check all this if the sum of all of these powers is equal to 0. So just to make sure, 144, 48, 48 minus 8 plus 56 is 0. So seems like we did everything correctly.
Will you explain the CCVS again?
Sure. So it is a current controlled voltage source, okay? So let me draw. So we have a dependent source because it's denoted by the diamond or rhombus or whatever shape you care to call that thing, okay? Anytime we have one of those, that means that this plus and minus sign, which means it has a positive and negative polarity terminal associated with it. That's how we tell that it's a voltage source. It said my internet connection was unstable, so how much of what I just said got cut off?
I didn't
A
hear.
little bit.
All right, so the plus and the minus sign means that it's a voltage source, okay? So this is a current controlled voltage source, and I can identify that by the fact that there is some number multiplied by a current, right? So this is 1 multiplied by the quantity Ix. So for a current controlled voltage source, there is going to be a trans resistance R multiplied by some current Ix. The implied units of this coefficient R are volts per amp. And the reason for that is because this is a voltage source, so it is going to be supplying voltage to the circuit. Even though the controlling quantity is a current, what it does is it converts that current to a voltage and then supplies that voltage to the circuit. Did that help clarify anything?
I believe so.
Okay.
How did you
Thank
get
you.
4 for the IX?
So right here, it literally says Ix is equal to 4.
Thank you.
No problem. Any other questions?
I'm good.
All right, so that was the last problem for the in-class assignment. We went through that pretty quick. Have any of you guys had an opportunity to look at your web work or anything yet? Oops, that was the wrong computer.
Yep.
Anybody have any questions about the web work or anything for those of you that have had an opportunity to go through it? So let me talk briefly about the web work. So I opened up all of them, I think it was yesterday, and they're all due at the end of the quarter, which I don't have a problem with because that means I don't have to reopen things and give people extensions and all that kind of junk because they're not keeping up with stuff. The issue is that if you guys don't stay on top of things, it's going to be very easy for you to fall behind in the class. So the expectation going into these example problem working meetings or whatever is that you'll, at a minimum, take a look at the web work problems beforehand. Not fully go through them or anything, but so maybe I should ask a question. Mr. Cuccinella, you have raised your hand. What's up?
Yes, sir. So do you know exactly like which, because I see that since you did open all of them, is there like which homeworks are due before, or like not, I know they're all due at the end of the quarter. What I should say is which ones cover up to the first exam and then the second exam and so forth.
Okay, so lectures 1 through 8 are on the first exam, which mean homeworks 1 through 8 are on the first exam. So practical sources is the last thing we'll cover for exam 1. The last transient analysis will be the last material that we'll cover for exam 2. I believe that's lecture 15. And then lecture 3, I still need to post that poll or whatever on Moodle. I forgot about that, to see how you guys were leaning towards cumulative versus non-cumulative to get an official tally there. But so to reiterate, homeworks 1 through 8 and in-class assignments 1 through 8 are good for exam 1. And actually, let me pop off my desk real quick and write myself a note on my to-do list to put up practice tests. So I'll be back in just a second.
Does anyone know where he put that poll, or has he even opened it yet?
I haven't opened it yet.
What poll is it?
Thanks.
No, not yet.
Okay. Yeah, so I have not put up the poll yet, but I will do that today. As soon as I get off this meeting with you guys, I'll do it so I don't forget about it. I'll also post some old tests. So my old tests that I'm going to post, there'll only be a couple of them, but they'll be very representative of the type of material that you should expect on your exam. They're similar to the in-class assignments and all that kind of stuff, maybe a little more so than the homework sets. Just because I made the in-class assignments, I didn't make the homework sets. Excuse me. But yeah, if you have any questions about any of those problems or the web work or the in-class assignments or anything that's troubling you in circuits, that's what these sessions are for. So anybody got anything else they want to talk about?
When will you post the submission thing for the in-class example work?
Within the next 10 to 15, or within 10 to 15 minutes of us wrapping this Zoom meeting up.
All right.
Is this still like a homework binder thing going on? I don't know if it ended or not.
Yeah, because it's online and also because it's a summer class, I'm just gonna say no, because that seems like a lot of work and I don't want to do it. So instead, I think it says something about that on the syllabus, but I think I also mentioned in the first Zoom meeting that instead of doing that, I'm just going to calculate, like all 15% of your homework grade will come from your web work score. So I won't collect a binder because it just seems like an awful lot of work and I don't want to deal with it. Okay. Any other questions? All right, nobody appears to be saying anything, so I'm going to take care of those things. And I've also recorded lecture 2. I just need to edit that, and it should be up before I head home at 5. So you should have several hours to look over it before class at 10 tomorrow. So have a good rest of your day, and if you have any other questions or anything pop up, just shoot me an email.
Thanks, Dr. Hartman.
Thank you.
Thank you.
Thank you.
See you guys later. Have a good rest of your Monday.
You too,
Thank
sir.
you too. How do I get rid of this crap?